Welcome to Master Concepts in Chemistry. In this lesson, we will discuss the four quantity numbers used to describe an atomic orbital or an electron's cloud. The first is called the principal quantity number. It has a symbol lowercase n. The second is called the angular momentum quantity number. It has a symbol lowercase l. The third is the magnetic quantity number. It has a symbol lowercase m and lowercase l as a subscript. And the fourth is the spin quantity number. It has a symbol lowercase m and lowercase s as a subscript. So what is the principal quantity number? The principal quantity number specifies the energy level. As a result, it is important in determining the energy of the electron. Usually, it takes values from 1, 2, 3, and so on. It doesn't take 0. It only takes values from 1, 2, 3, and so on. It doesn't take 0. Sometimes the principal quantity number is referred as a shell, and within it you have subshells, and these subshells are specified by the angular momentum quantity number. So the angular momentum quantity number determines the shape of the orbitals. And usually, it takes values starting from 0 all the way to n minus 1, where the n here means the principal quantity number. So as you can see, values of the angular momentum are limited by values of the principal quantity number. Okay. The next is the magnetic quantity number. The magnetic quantity number determines the direction of orbital in space. That means it determines the orientation of the orbitals in space. And also, it specifies the different types of orbitals that we have. And usually, the values of the magnetic quantity number starts from minus L through 0 to plus L. And its values are limited by the angular momentum. And what is the electron spin? The electron spin determines the spin of the electron. So it can only take two values, plus half or minus half. Now, as we've seen, we have four quantity numbers. So there's no way you would have electrons that will have all the four quantity numbers the same. Usually one of them will be different. Okay, so let's look at how to generate quantity numbers. So here I have principal quantity number. So principal quantity number has a symbol n, and it takes values from 1, 2, 3, and so on. And the angular momentum quantity number has a symbol lowercase l, and it takes values from 0, 1, 2, all the way to n minus 1. Okay. And remember, the n minus 1 is the n here is the principal quantity number. So the values of the angular momentum, of course, are limited by the value of your principal quantity number. And the magnetic quantity number, as we know, has a symbol m, l, and it takes values from minus l through 0 to plus l. Okay, and the l here is the angular momentum. So values of the magnetic quantity number is limited by values of the angular momentum. And the electron spin, which represents ms, can only take two values, plus half or minus half. Okay, so let's assume we have our principal quantity number to be n equal to 1. What are the possible values of our angular momentum? So the possible values for angular momentum, of course, is going to be 0, because angular momentum has values starting from 0 to n minus 1. So n minus 1, or n is 1, so 1 minus 1 is 0. So that means that we can only have 0 as a value for our angular momentum. So what then would be the corresponding value for our magnetic quantity number when L equals to 0? It's also going to be 0, because minus L here will be 0, then 0, then plus 0. So it's basically zeros throughout. So it's only going to be 0. Okay. And what are the possible values for our electron spin? It can be plus half or minus half. So that means an electron can have values of 1, 0, 0 plus half, or 1, 0, 0 minus half. So if you have two electrons in an orbital, one of them will have values of 1, 0, 0 plus half, and the other will have values of 1, 0, 0 minus half. So you can have two electrons having all the four quantum numbers the same. So if the first three are the same, but the last one will be different for the two. Okay, so keep that in mind. So now, let's say we have our n equals to 2. We have n equals to 2. What are the possible values for angular momentum? Remember, angular momentum starts from 0 to n minus 1. So our n here is 2. So 2 minus 1 is 1. So including the 0. So that means that when n equals to 2, we can only have two values of our L, 0 and then 1. So you see that. Now, we've already seen that when our angular momentum is 0, our magnetic quantum number, of course, is going to be 0. Okay, and then possible values for our electron spin is going to be plus half or minus half. Or minus half. Okay, so an electron can have values of 2, 0, 0 plus half. Another can have values of 2, 0, 0 minus half. Okay, so when our angular momentum is 1, what are the possible values for our magnetic? So our magnetic is minus L 0 plus 1, minus L through 0 plus 1. So just like a number line, you follow a number line. So when it's minus 1, the next value will be 0 and then plus 1. Okay, so since our L is 1, then that means that our first value will be minus 1, and then the next value on the number line will be 0, and then the next value will be plus 1. Okay, so that means that when L, angular momentum, is equal to 1, then that means that our magnetic quantum number will have values of minus 1, 0, plus 1. Okay. So, what are the possible values of electron spin? Again, the same thing. So, plus half or minus half. That is when our magnetic quantum number has a value of minus 1. And when our magnetic quantum number has a value of 0, the electron spin can be plus half or minus half. And then when it's plus 1, it can be plus half or minus half. So you see, so the electron spin is easy. Now we do have names for the angular momentum quantum numbers. Okay, so remember we said the angular momentum specifies a type of orbital. So usually when it's 0, when L is 0, we normally say it is the s orbital. S orbital. When L is 1, we usually say it is the p orbital. P orbital. Okay. S means sharp and P means principal. Okay. So S means sharp and P means principal. And P means principal. So when L is 0, it means the s orbital, and when L is 1, it means the p orbital. Now, as you can see here, the p orbital, remember the magnetic quantum number tells you the different types of orbitals you have. So as you've seen, we only have 0 corresponding to when L equals 0. So we only have one type of s orbital, Now, when you look at when L equals to 1, when angular momentum is 1, we have how many values for our magnetic quantum? We have 3. So that means that we have 3 different types of p orbitals. So when L equals to 1, we have 3 different types of p orbitals based on the values of our magnetic quantum number. So the first p orbital is px, the next is py, and then third is pz. Okay, so we have 3 different types of p orbitals. And remember, each of these p orbitals will take a maximum of 2 electrons. So that means that to fill these 3 p orbitals completely, you need 6 electrons, a maximum of 6 electrons. Okay. So now let's move on to when n equal to 3. So we've looked at the s orbital, we've looked at the p orbital. So now I want to look at the others. Okay. So when n is equal to 3, what are the possible values of our angular momentum? Remember, I start from 0 all the way to n minus 1. So that means that our values would be 0, 1, and the n minus 1, that is what? 2. So you see that, 2. And remember, the angular momentum specifies the type of orbital. So again, we've looked at 0, which is s orbital, 1, which is p, and then 2 now is the d orbital. Okay, d orbital. D means diffuse. So if you look at possible values of our magnetic quantum number will have values of starting from -2. We are following the number line again. So -2, the next value will be -1, and then 0, +1, and then +2. So we are going all the way from -2 to +2. Okay, so let's count how many values of magnetic quantum number we have. So we have 1, 2, 3, 4, 5. So 5 different values of our magnetic quantum number, meaning we have 5 different types of what? D orbitals. Okay, and each of these will take a maximum of 2 electrons. So that means that to fill all the D orbitals up, you need a maximum of 10 electrons. Okay, and again, the electron spin. So each of these values would correspond to +½ or -½ electron spin for the electron quantum number. Now let's look at the last one here. The last one is when n is equal to 4. So when n is equal to 4, when our principal quantum number is equal to 4, what are the possible values that we can have? So we can have again 0, 1, 2, and n minus 1, which is 4 minus 1, that is 3. So we've looked at this, which is the s orbital. We looked at 1, which is the p. We looked at T2, which is the D. Now we'll look at 3. 3 is the F orbital. So this is the F orbital. F means fundamental. Okay. So what are the possible values for our L equals to 3? So the possible values, magnetic quantum number values for our L equals to 3 would be starting from -3, -2, number line, -1, 0, +1, +2, and +3. So let's count how many we have. How many values? We have 1, 2, 3, 4, 5, 6, 7. So we have 7 different types of F orbitals. So each orbital would take a maximum of 2 electrons. So in total, we would have to fill all the F orbitals up, which of course are 7 with 14 electrons. Okay, so so that is that. And again, to generate the electron spin for each of these values, it could either be +½ or -½ just like we saw. Okay, so now let's look at a problem to apply what we've learned. So here, the question says that you have what is wrong with each of the following quantum numbers and their corresponding names. Okay, so these are the names. So we want to see which values make sense and the ones that don't. So let's start off with A. So A here, we know N means our principal quantum number. We know L means our angular. We know ML means our magnetic. And we know MS means our spin. And the name that we get, the names of the orbitals correspond to our values of L. And then the numbers in front of the orbitals correspond to the values of the principal quantum number. Okay, so let's start. So here our N is equal to 1. So when N equals to 1, L can only have a value of 0. So here we have 1 here. So 1 is not supposed to be here. So that is wrong. Okay, so 1 is not supposed to be there. So it's not possible because values of your principal quantum number limits the values of your L. So 1 is not supposed to appear under our angular momentum. So that is not supposed to be there. Okay. Now let's move on. Yeah, so 0 is fine because when L, yeah, so 0 is fine. MS also is fine. +½ or -½ is fine. And then the name. The name, of course, makes sense in the sense that if L is 1, that means that it's P, right? And then our N is 1. Okay, so, but the fact is that here is not supposed to be 1. Okay, so, yeah, so the name also, though P means L equals 1, but 1 is not supposed to be here. Okay, so, yeah, we'll see this also doesn't make sense. Okay, now let's move on to B. B, we have N equals to 4. Yes, and we have L equals to 3, so that makes sense. Okay, and then when N equals to 3, what does that mean? That means that in terms of the names of the orbitals, when N equals to 3, that's an F orbital, right? Yeah. +1, yes. -½ that's fine. And then 4 here means, the 4 means the principal quantum number, which is 4, that's fine. But the D here doesn't correspond to the name of our L equals to 3, because when L equals to 3, that's an F orbital, but here we have a D. So the name doesn't make sense. Okay, so 4D is not right. Now let's move on to the next. We have our principal quantum number being 3, our L is 1. That's fine, because 1 is a possible value when n equals to 3. Now ML is -2. This doesn't make sense, because when L is 1, that means that ML can take values of -1, 0, and then +1. So there's no 2 in here. So this is not right. Okay. +12, yeah, that's fine. Now 3p. 3 here signifies the energy level. The principal quantum number 3 is fine. And then P here signifies the 1 here, the name of our L, which is P. So the name is fine. But just that the magnetic quantum number is not right. The -2 is not right. So this is wrong. So yeah, so you see how we analyze it. So once you understand how to generate the quantum numbers, you can easily, analyze a problem and figure out what is wrong with it.